Hi guys, so today we're going to keep it pretty short and sweet. We just wrapped up scalars and vectors, and we're going to be talking about speed, velocity, and acceleration today. So again, these topics for today are just more of the basics for kinematics. And once we get through these basics, we'll start tying them all together. So this is not necessarily directly related to what we talked about last class, but it will come together after we get all of our base knowledge down. So we're first going to talk about the difference between speed and velocity. So if you look at speed, the variable for speed is still a v. There's no arrow on top of it, which means that it is a scalar quantity. So speed does not have a direction associated with it, which means it's a scalar quantity. So again, we talk about average speed here. We talked about average speed a little bit last lesson. So anytime you're looking for your average speed, you want to know your distance divided by the time, which is what this formula is showing you. So V is for speed in this case because there's no arrow on top of it. And then AV is your subscript, means average. So your average speed is going to be here, and that is equal to the distance divided by the time. So just pay attention to these units. Anytime you write speed, it needs to be in meters per second or kilometers per hour. So that correlates here with these. So distance should always be in meters or kilometers, and then time should always be in seconds or hours. You could have meters per hour or kilometers per second, but that's not typically the notation that's asked for. So if you have one of these, if this is kilometers on top and it's seconds on bottom, you need to convert one into the other so that you have some cohesive units here. So speed is going to be V equals D over T. So distance divided by time. Velocity is darn near exactly the same formula. So we have the same setup here, except you notice this has a little hat on top, and so does this one, little arrows. So that's designating that they're vectors. And that there should be a direction associated with those. So again, same units here for velocity, and 9 times out of 10 in physics, we're using the velocity, not just the speed. So almost all of the time we'll be associating a direction with things. So here, same units, we have kilometers per hour or meters per second. So your average velocity is going to be the change in distance divided by the change in the time. So your basic velocity formula is velocity is density, sorry. Velocity is distance divided by time. So here's some examples. So one example of just speed, and you can tell that it's speed because there's no arrow on top of the V. What was his average speed? Same formula though. So over here on the side, this is what we're given. We have distance is 100 meters. The change in time was 9.58 seconds, and we're looking for the average speed. So we're plugging that in. So you have your distance on top, speed on bottom, you divide it and get 10.43.8 meters per second. Velocity, on the other hand, we do have a direction associated with that, so you need to include that in your work and your answer. So velocity has a little arrow on top, the little vector hat. And so we have here a plane travels 376 kilometers in southeast in 5.2 hours. What was the plane's average velocity? So you could do this if you go on a trip on an airplane. So we have the change in distance was 376 kilometers southeast. The change in time was 5.2 hours, and these two units go together, so kilometers per hour. And then we're finding the average velocity. So we're plugging that into our formula again. So we have distance on top, and since this is a vector, we're including the direction in our notation here. So we have 376 kilometers southeast divided by 5.2 hours. You divide that, and you should have your average velocity is 72.31 kilometers per hour southeast. Now we're going to switch to acceleration. So acceleration includes velocity. That's why it was important to go over that first. So acceleration is talking about the rate of change of velocity. So how fast or slowly does your velocity change? Are you speeding up? Are you slowing down? So you have these formulas. This is the expanded version of the same formula down here. So you have acceleration, and acceleration has a little hat on top because it is a vector quantity with a direction. You have the final velocity. So V2 is final, V1 is initial. So you have final velocity minus initial velocity over final time minus initial time. So that can also be written like this, the change in. So if you have the change in velocity over the change in time. So if we're going to look at the units for this, for acceleration, what units would you use? It ends up being meters per second squared, which is this down here. So m/s squared. And the reason for that is because we're using velocity within here. So if you look at the units that you'd have attached to these variables, you'd have meters per second minus meters per second over second minus second. So when you break that down, you end up having meters per second per second. So instead of saying that meters per second, it's written as meters per second squared. So when you are looking at acceleration, it is important to designate which direction is positive and which direction is negative if you have things going in opposite directions. Because when you're talking about velocity and acceleration, you might have an initial velocity that's in the positive range, and then you are slowing down, and you could even have a negative velocity technically. So if you have, depending on what direction you're going, I guess I should clarify. So just like you had with your displacement from last class and the position, you had to pay attention to what direction you were moving back and forth, and you'd subtract or add your distances depending on that. It's the same thing for acceleration. So you always want to make sure that you are defining and using positives and negative directions with your velocities as you work. So that being said, there's a pattern that's usually followed. So anything that says that it's moving in a forward direction is usually a positive number, and backwards will be negative. And then if you're looking at directional notations, you're going to say that north and east, so north and east are usually your positive directions, and then south and west are typically your negative directions. So it will not always be this way, and it might be more logical if you are looking at this on kind of like a different plane, that you might say that south is going to be your positive position because maybe you're driving south initially. So that'll kind of depend on the question, but almost always you're going to use these as your positives and negatives when you're looking directionally. So another thing to look out for with acceleration is oftentimes it will not give you all of the pieces you need as numbers. So you might say that your car, you were stopped at a stop sign and you started driving, and you accelerated until you hit 30 meters per second. And you might be trying to find your acceleration. So when it says that you're going from rest or you're going to a stop, that would be your key phrase indicating that the velocity was 0 at that point. So another example is this: a horse race begins from rest with an acceleration of 2.2 meters per second squared north. What is the horse's velocity after 5.8 seconds? So the pieces you need for this would be your initial and final velocity, and then acceleration and time to be able to plug it into that formula. What you are not given here is your initial velocity, not in numbers. So if you look at this, what would your initial velocity be? Well, it would be 0 because you're starting from rest. So just pay attention to that. Normally your information is there, you just have to look for it. So here's an example here. So we were talking about the horse that was starting at rest, and he came up to an acceleration of 2.2 meters per second and in the time frame of 5.8 seconds. So we're using our acceleration formula here. You can do this one of two ways. You can rearrange your equation first and then plug your numbers in to solve, or you can plug your variables in and solve for the missing variable. Either way should work fine. Sometimes later on down the line, it works a little better to find your formula first, but either way should be fine. So in this case, we went ahead and derived the formula that we were looking for. So we're breaking this down. We know we're solving for the final velocity. So if this is your given equation, we're solving for V2. We're first going to multiply time on both sides to remove it from over on the right side. So now we have acceleration times the change in time set equal to the final velocity minus the initial velocity. So then we want to get rid of this initial velocity so that V2 is by itself. So we're going to add initial velocity to the other side to get our derived formula. Okay, so now we have a formula where when we plug all of our variables in, we're going to end up with our answer. So that's what we did here. So we added in 2.2 meters per second squared north, that is acceleration, times the time, the change in time was 5.8, plus your initial velocity was 0 meters per second, and then that's going to equal velocity, the final velocity. So when you do all of your math here, pretty simple, you're just multiplying these values. You are going, or sorry, multiplying and then adding, you're going to end up with 12.76 meters per second north. So your final velocity, you could say, is about 13 meters per second north, which would just mean that after 5.8 seconds, you have accelerated at this rate. So after 5.8 seconds, your final velocity would be that the horse is going 13 meters per second in the direction of north. Another example, a hockey puck with an initial velocity of 65 kilometers per hour west ricochets off the boards. After 0.76 seconds in contact with the boards, its final velocity is 47 kilometers per hour east. Determine the acceleration of the puck. So you are given a lot of information here. You have the initial velocity, you have the time, and you have the final velocity. So we are going to just plug that right into our acceleration formula. Okay. So in this case, east is going to be positive and west is going to be negative. So I know there's a lot on this screen, so let's start with the very top. Okay, so we have the initial velocity was going 65 kilometers per hour west, and then our final velocity, you're going 47 kilometers per hour east because it says it ricocheted. So the hockey puck bounced off the side and changed direction. So what all the rest of this is converting the units because time is in seconds and acceleration, the unit for acceleration is meters per second squared. So we need to make sure that our units are correct to match that before we begin. So if we have 65 kilometers per hour, you can change this with dimensional analysis. This is basically dimensional analysis here. It's just written a little bit differently. So if you have 65 kilometers per hour, you could set that equal to 1 kilometer on bottom. 1 kilometer is going to be equal to 100 meters. And then meters is where we're going to end there. So then we can come back in here and say hours. So 1 hour would go on top and seconds would go on bottom. So basically what you're doing is you multiply across the top and then multiply across the bottom to get your final answer here and then divide. So you'd have 65 times 1,000 times 1 divided by 1 times 3,600. So what you end up with is 18.05 meters per second. Okay, so all we did was convert the 65 kilometers per hour into meters per second. We did the same thing down here. So 47 kilometers per hour, we're going to convert those units into meters per second, so 13.05. So this is what we're working with from here on out are these numbers. So for acceleration, we know we're going to use this formula. So we have final velocity minus initial velocity over the change in time. So we know that our final velocity is 13.05. That's what we put here. The initial velocity is 18.05, which is what we put here. So we're subtracting the two, and that's all over the time. We can get that to go away. Oh, there we go. All that over the time. So then you would just simply do your math. So you'd have 13.05 minus 18.05 over 0.76, which would give you an acceleration of 40.9 meters per second squared. So they went ahead and rounded that up here, probably to fit sig figs. So your acceleration is about 41 meters per second squared east. So I know that was a lot. That was a big chunk of information because we had to do all these conversions. But just make sure that you do that. It's important to change all of your units before you start with your problems, or else your numbers will be a mess at the end. It won't work. And that's it. So hopefully you guys feel comfortable with that. I know acceleration can be a slightly tricky sometimes, but I think the assignment today will help you understand that a little bit better. Just make sure that you're looking at these formulas and putting things in the right places, that your second velocity, so your final velocity is what goes first and the initial goes second, and then the change in time goes on the bottom. So units are important. Pay attention to units. Make sure that they're the appropriate units before you start doing your math, and make sure you have the correct units on your answers, along with the directions if it is a vector. So please let me know if you have any questions.